Today we'll discuss ISI's B-Math 2010 subjective paper, and the first question is, prove that in each year the 13th day of some month occurs on a Friday. Now what we'll do is, first we'll write number of days in any given month. So we'll start from January, February, March, April, May, June, July, August, September, October, November and December. Now in January we have 31 days, February we have 28 or 29 days, March 31, 30, 31, 30, 31, 31, 30, 31, 30 and 31 days. Now since we have two choices in February, we'll discard these two cases. Now what we'll assume is, we'll say, suppose March 13 is assigned 0 modulo 7. So this 0, it could represent any day in a week on March 13. Now from March 13 to April 13th, we have 31 days. And if we take 31 modulo 7, then 31 modulo 7 is 3. Now from 13th March to 13th May, we have 61 days. And if we divide 61 with 7, we get remainder 5. So on 13th May, it will be 5 modulo 7. Now till 13th June, it will be 92, and 92 is 1 modulo 7. So it will be 1 modulo 7. In the same way, till July, it will be 6 modulo 7. Till August, it will be 2 modulo 7. And till September, it will be 4 modulo 7. So if we look at all the modulos, then we have 0, 1, 2, 3, 4, 5 and 6. That means from March to September, there will be some month which will have Friday on its 13th day. Now question number 2 is, in the accompanying figure, y equals fx is the graph of one-to-one continuous function. At each point P on the graph of y equals 2x square, assume that the areas OAP and OPB, they are equal. Here PA and PB are the horizontal and vertical segments. Determine this function f. Now suppose this point is y0, and here x will be under root y0 by 2. Then this point A, it will be some x0 and y0, and here this point B, it will be under root y0 by 2 comma y0 by 2. Now first we'll calculate this area of OPB. Now area of OPB, it will be simply this integral from 0 to under root y0 by 2 and then upper curve minus lower curve. So 2x square minus x square will be simply x square dx, which is 1 by 3 x cube. So we can write this as 1 by 3 and then y0 to the power 3 by 2 and 2 root 2. So this area, it will be y0 to the power 3 by 2 upon 6 root 2, and that's our first equation. Now we'll find this area OAP. Now this curve is under root y by 2 and this curve is f inverse y. Now we'll find this area with respect to y axis. So area of AOP will be this integral from 0 to y0 and then upper curve, which is under root of y by 2 minus f inverse y dy, and that's our second equation. And the question, it says these two areas, they're equal, so we can write this integral from 0 to y naught under root y by 2 minus f inverse y dy, it will be equal to 1 upon 6 root 2 y naught to the power 3 by 2. Now what we'll do is we'll differentiate both sides with respect to y naught. So if we differentiate it, we can write under root of y naught by root 2 minus f inverse of y naught. It will be equal to 1 upon 6 root 2 3 by 2 into under root y naught. Now here 3 and 6 will cancel, so it will be 1 upon 4 root 2. So we can write this as under root y naught upon root 2, and here will be 1 minus 1 by 4, and it is equal to f inverse of y naught. Now this is 3 by 4, so this f inverse y naught will be 3 under root y naught upon 4 root 2. Now we can also write this as f 3 under root y naught upon 4 root 2, and this is equal to y naught. Now what we'll do is we'll let 3 under root y naught upon 4 root 2 as x, then y naught will be 16 into 2 32, so it will be 32x square by 9. So we can write this function f as fx equals 32x square by 9. So this function is given by 32x square by 9. Now the third question is, show that for any positive integer n, the sum of 8n plus 4 consecutive positive integers cannot be a perfect square. Now suppose these integers are a plus 1, a plus 2 up to a plus 8n plus 3. Now if we find their sum will be 8n plus 4 divided by 2 into a plus l, which is 2a plus 8n plus 3. Now we can write this as 4n plus 2 into 2a plus 8n plus 3, and it says we have to prove that it cannot be a perfect square. Now suppose it is some perfect square of any integer, say L square. Now we simplify this left hand side, we can write 8an 32n square 12n 4a plus 16n plus 6, and this is equal to L square. Now if we take LHS modulo 4, LHS is congruent to 2 modulo 4, and we know that any perfect square, it is congruent to 0 or 1 modulo 4. So left hand side, it cannot be equal to its right hand side. So sum of any 8n plus 4 consecutive positive integers cannot be a perfect square. And this is how we solve such questions. Now question number 4 is, if ABC belongs to 0 and 1 and a plus b plus c equals 2, then prove that ABC upon 1 minus a, 1 minus b, 1 minus c is greater than or equal to 8. Now what we'll do is, we'll let 1 minus a as capital A, 1 minus b as capital B, and 1 minus c as capital C. Now if we'll add them, we'll write 3 minus a plus b plus c, and is equal to capital A plus capital B plus capital C. Now a plus b plus c is 2, so 3 minus 2 is 1. So value of capital A plus b plus c is 1. Now we'll change this inequality in terms of capital A, B, C. So in the numerator we'll have a, which is 1 minus a, so it'll be 1 minus A into 1 minus B into 1 minus C, and it'll be greater than or equal to 8 into, and this is ABC. Now we'll multiply these three brackets. We can write 1 minus A plus B plus C, and then plus AB plus BC plus CA minus ABC, and it'll be greater than or equal to 8ABC. Now A plus B plus C is 1, so this 1 and 1 will cancel. We can write AB plus BC plus CA, it is greater than or equal to 9ABC, and if we divide everything with ABC, we can write 1 upon A plus 1 upon B plus 1 upon C, it is greater than or equal to 9. So we have to prove this result. Now for these three numbers A, B and C, if we write their arithmetic mean will be A plus B plus C divided by 3, and it'll be greater than or equal to its harmonic mean, which is 3 upon 1 by A plus 1 by B plus 1 by C. Now A plus B plus C is 1, so this is 1 here. So from here we can say 1 upon A plus 1 upon B plus 1 upon C, it will be greater than or equal to 9, and this is the answer to this question. Now question number 5 is, let A1 be greater than A2 be greater than AR, then we need to find this limit, which is limit n tends to infinite A1 to the power n plus A2 to the power n plus AR to the power n to the power 1 by n. Now we know that we can write this A1 as A1 to the power n to the power 1 by n, and it will be less than A1 to the power n plus A2 to the power n plus AR to the power n whole to the power 1 by n. Now each of AI, it is always less than A1. So it will be less than R into A1 to the power n to the power 1 by n. So from here we can write A1 is less than A1 to the power n plus A2 to the power n plus AR to the power n to the power 1 by n will be less than R to the power 1 by n into A1. Now we'll take this limit n tends to infinite. Now this limit is A1. This limit is also A1. So from sandwich theorem, we can say that the value of this limit will be simply A1. Now question number 6 is, let each of the vertices of regular 9-gon be colored black or white. Now first part is, show that there are two adjacent vertices of the same color. Now what we'll do is, suppose there are no two adjacent vertices of same color, and suppose we start with black. So if this is black, then here it'll be white, again black, white, black, white, black, white, and then it'll be black. So if we start with black, there'll be two adjacent vertices which are black, and if we start with white, then we'll end up having at least two vertices which are white. So in any case, there'll be two adjacent vertices of the same color. Now in part B, we have to show that there are three vertices of the same color forming an isosceles triangle. Now we'll prove this result using contradiction. So what we'll assume is, we'll suppose that there are no three vertices of same color forming an isosceles triangle. Now without loss of generality, we'll assume this vertex to be, suppose, black. Now this is black. Now these two adjacent vertices, they cannot be black. If they are black, then we'll have this triangle as isosceles triangle. So we have two possibilities. Either one of them is white and other one is black, or both of them, they'll be white. Now let us come to this first case. Now if this is white and these two are black, now this cannot be black. It has to be white. Otherwise, again we'll have this isosceles triangle. Now if we talk about this vertex, then this vertex will be either black or white. Now if it is black, we'll have this isosceles triangle, and if it is white, we'll have this isosceles triangle. So in either case, we'll have an isosceles triangle. So that means this condition is not possible. Now, what about this case? When we have white, black and white. Now, if it is white, black and white, these two, they cannot be white, because if it is white, then we'll have isosceles triangle. So this one, it should be black, and here also it should be black, because if it is white, then we'll have isosceles triangles. But if we choose them as black, then we have this triangle which is isosceles. So here also we have this case where we have isosceles triangle. So in any case, we'll always get an isosceles triangle. So from contradiction, we can say that there are three vertices of same color forming an isosceles triangle. Now question number 7 is, let ABC be real numbers and assume that all the roots have same absolute value, then show that A is 0 if and only if B is 0. Now suppose the roots are Z1, Z2 and Z3 and they have same modulus. So that means mod Z1 equals mod Z2 equals mod of Z3 and it is equal to say K. Now we square it, we can write Z1 Z1 bar equals Z2 Z2 bar equals Z3 Z3 bar and it is equal to K square. So we can write 1 upon Z1 is equal to Z1 bar by K square. 1 upon Z2 is Z2 bar by K square and 1 upon Z3 is Z3 bar by K square. Now if we write S2, S2 is sum of roots taken 2 at a time. So it will be Z1 Z2 plus Z2 Z3 plus Z3 Z1 and it will be equal to B, and suppose B is 0. So it will be 0. Now if we divide it with Z1 Z2 Z3, we can write 1 upon Z1 plus 1 upon Z2 plus 1 upon Z3 and it will be 0. Now 1 upon Z1 is Z1 bar upon K square. So we can write 1 upon K square Z1 bar plus Z2 bar plus Z3 bar and it will be 0. Now we take its conjugate, we can write Z1 plus Z2 plus Z3 is 0. Now this is nothing but sum of roots, which is minus A. So from here we can say value of A, it must also be 0. Now if we start from A equals 0, we can prove that B is 0. Now question number 8 is, let f be a real value differentiable function on the real line such that limit x tends to 0, fx upon x square exists and is finite. Prove that f dash 0 is 0. Now it is given that f is a differentiable function. So that means it is continuous also. Now if the function is continuous, we can write f0 as limit x tends to 0 fx. Now we can write this limit as limit x tends to 0 x square into fx by x square. So it will be limit x tends to 0 x square into limit x tends to 0 fx by x square. Now this is finite and it is 0. 0 into finite is 0. So value of f0 is 0. Now if f0 is 0, we can find f dash 0 as this limit h tends to 0 fh minus f0 upon h. Now f0 is 0. So we can write this as limit h tends to 0 h into fh upon h square. Now fh upon h square is finite and h is 0. So from here we can say f dash 0, it must be 0. Now question number 9 is, let fx be a polynomial with integer coefficients. Assume that 3 divides the value fn for each integer n. Prove that when fx is divided by x cube minus x, the remainder is of the form 3rx, where rx is a polynomial with integer coefficients. Now we can write this polynomial fx as x cube minus x into gx plus ax square plus bx plus c, where a, b, c are integers. Now if we find f0 is c, and it says 3 divides value fn for each integer n. That means 3 divides c, and if 3 divides c, then c is of the form sum 3k1, where k1 belongs to z. Now if we look at f1 is a plus b plus c, and again 3 divides a plus b plus c. Now 3 also divides c. From here we can say 3 divides a plus b. In the same way, if we find f minus 1, it will be a minus b plus c, and again 3 divides a minus b plus c, or we can say 3 divides a minus b. Now a and b, they can be of the form either 3k or 3k plus 1 or 3k plus 2. Now 3 divides both a plus b and a minus b if and only if both are of the form 3k. So that means this a, it must be some 3k2, and this b, it must be some 3k3. So this remainder, it will be of the form 3k2 x square plus 3k3x plus 3k1, or if we take 3 common, it will be k2x square plus k3x plus k1, which is of the form 3rx, where k1, k2, k3, they are integers. So we have proved that when fx is divided by x cube minus x, its remainder is of the form 3rx, where rx is a polynomial with integer coefficients. Now question number 10 is, consider a regular heptagon a, b, c, d, e, f, g. Now prove that 1 upon sine pi by 7 equals 1 upon sine 2 pi by 7 plus 1 upon sine 3 pi by 7. Now if we rearrange it, we can write this as sine 2 pi by 7 into sine 3 pi by 7 will be equal to sine pi by 7 into sine 2 pi by 7 plus sine pi by 7 into sine 3 pi by 7. Now we'll multiply to both sides. Now this is 2 sin A sin B, which is cos A minus B minus cos A plus B. So it will be cos A minus B, which is cos pi by 7 minus cos A plus B, which is cos 5 pi by 7. Now this is cos pi by 7 minus cos 3 pi by 7, and this one is cos 2 pi by 7 minus cos 5 pi by 7 minus cos 4 pi by 7. Now cos 4 pi by 7 is cos pi minus 3 pi by 7, and cos pi minus theta is minus cos theta. So these two expressions, they'll cancel, and cos 2 pi by 7 is minus cos 5 pi by 7. So this left hand side, it is equal to its right hand side. So we have proved that 1 upon sine pi by 7 equals 1 upon sine 2 pi by 7 plus 1 upon sine 3 pi by 7. Now using A or otherwise, show that 1 upon AG equals 1 upon AF plus 1 upon AE. Now suppose this center is at O and we complete this triangle. And we complete these triangles. Now this angle is 2 pi by 7 and this is suppose radius r. Now using cosine rule we can write cos 2 pi by 7 equals 2r square minus ag square upon 2r square, or ag square is 2r square 1 minus cos 2 pi by 7. Now 1 minus cos theta is 2 sin square theta. So it will be ag square equals 2r square into 2 sin square pi by 7. We can write this ag as 2r sin pi by 7, or sin pi by 7 equals ag upon 2r. Now for this triangle, angle is now 4 pi by 7. So we'll get AF as 2 pi by 7 equals AF upon 2r. And in the same way, this is 6 pi by 7. So we write sine 3 pi by 7 as AE upon 2r. Now we'll put the value of sine pi by 7, sine 2 pi by 7 and sine 3 pi by 7. So we can write this as 2r upon AG equals 2r upon AF plus 2r upon AE. Now 2r will cancel. So from here we can write 1 upon AG equals 1 upon AF plus 1 upon AE, and this is what we need to prove.